welcome. So in the last class we started our discussion about the polymerization strategy for LLDPE preparation, and today we will continue. In the last class we discussed the what are the strategy for the LLDPE, and we learned that we need to do the alpha copolymerization. So there are two copolymerization means there are two monomers. One is here the ethylene and one is the another alpha olefin, but with the shorter carbon atoms, not like a very large number of carbon atoms of alpha olefin. So today we will continue mainly the chemical structure, the design of the catalyst, and we will discuss that what are the very popular and famous catalysts which are used in industries and the laboratory, and we will try to discuss or understand the reaction mechanism involved in the oligomerization. Okay. So in concepts you will see that it will be continue. So we will try to understand mainly the here that is the catalytic cycle and mechanism, okay, and the catalytic systems. Okay. So that we will concentrate in today's class. So far what we have understood that there is a process in the soft process, that is the SHOP, the cell higher olefin process. So what are the steps? So first step is the oligomerization, that is basically the homogeneous catalytic system, and then is the isomerization, okay, to internal olefins, and the metathesis of lighter and heavier internal olefin, okay, and then eventually the last one is the hydroformylation and reduction. Okay. So it's basically you will see that we will be getting our desired alpha olefin from here. We need there is some purification steps are involved here, and here these steps is basically to use the byproducts to a useful materials that we discussed in our last classes. So we'll continue our discussion and we'll see that what are the basic steps in polymerizations, in oligomerations of the alkenes, let's say ethylene. So here you will see that these are the catalysts developed, nickel, all are like is a nickel based catalysts, which are the most effective catalyst here. So here you will see that in most of the cases you will see that here the phosphorus and oxygen donors, okay, and you will see this in most of the cases is a phosphinoacetate. So like here this is basically the phosphinoacetate, okay. So if you, so this is pH, these are the ligand, okay, and okay. So this you will see that this kind of mostly this kind of ligands like a phosphinoacetates or its derivative, and nickels is here. You will see that oxidation state is +2 here, okay, and this is the basically the coming from the cord, okay, after the oxidative addition. I will show how to what are the general synthetic protocols, but you try to understand that what are the chemical structure of these catalysts. Very simple, complex, very simple way to synthesize, but it's very effective as a first step of the soft process. Okay, so this is for the olefin oligomerations. Okay, so here you see the oxidation state. Here also this is a +2 oxidation state, nickel +2. Okay, and how to synthesize it. So this is all you see that mostly the phosphorus oxygen donors, and there will be one nickel carbon bond here. So this is basically nickel carbon bond, okay, this one, okay, and this one, okay, and this is the phosphorus, this is oxygen donor, and here there will be one more labile, okay. So this is either this one or either this one, okay. So this is quite labile in nature. It may be the alkene or it may be the phosphine, which can come out from the vicinity of the metal centers to get the space of the alkene, okay, for the reaction. So here you will see that it is very easy to prepare. So this is the nickel cord. So this is zero oxidation state, you know, and cord, you know, is very easy to synthesize. So we generally write the cord like this one. So this is the cycloocta diene. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8. So you can write 1, 5 cyclooctadiene. Okay, and if you take the phosphino acetic acid, so one cord is eliminated here. So this actually eliminates, because these are alkene is weakly bound. However, it acts as a chelating ligand. Okay, so that's why it is very easy to prepare. It's actually very good precursor for many for nickel zero complex, and which can be very easily prepared in lab. Okay, so then what you will see here, so you will these ligands, that is the PPH2 and CH2 COO, that is the phosphinoacetate, okay, and this H plus, okay, that is that OH, this one is basically the protonated here, and you will get the so it basically you can understand, you can see that here it is nickel 2 oxidation state. So this is 2, this is the anionic ligand, and this is the C minus here. So this is the nickel carbon sigma bond, and here nickel carbon pi bond, and here the nickel carbon sigma bond. Okay, and this is an equilibrium with, see, the allyl type of bond. So this is C3 allyl, and you will get this kind of a so it is in equilibrium. Okay, so the nickel catalyst is very easy to synthesize. You start from the nickel cord, add phosphinoacetate or any other phosphinoacetate derivatives, you can make your desired catalyst, and that's why it is so popular. Synthetically is easy and also very effective. Okay, so now you will see here, so this is the catalyst, this is my phosphorus donor, this is oxygen donor, this is alkene, and this my nickel carbon bond. As I told that there you will be, if you see very carefully, that in where case one phosphorus, one oxygen donor, one carbon donor, and one ligand is the labile. Okay, that is the basic chemical structure of the nickel 2 catalyst. Okay, so this is also preserved here. Here instead of the phosphine, you will see you have one alkene here. Okay, in this case the alkene here. Fine. So let's take one example. Okay, that this is the another way of synthesize nickel catalysts. Here the precursor is NiPPS3 whole 4. Okay, so this is also quite popular precursors. So I showed two examples. One is the nickel Cod2 and one is the nickel triphenyl phosphino tetrakis triphenylphosphino derivative of the nickel. Both are zero oxidation state here. So how you see here, you have a so after treating these phosphino acetates, okay, what you are getting this complex where it is nickel. You will see that this is my zero catalyst. Actually this is not real bond, this is just a weak interaction. So this is nickel zero catalyst. So 2 ppS3 is coming out. Okay, so coordination number is 4 here, and then 1 ppS3 is coming out, and what is happening here is basically happening the oxidative addition here. We are very familiar with the 4 unique reactions in organometallic chemistry, that is oxidative addition, reductive elimination, and the insertion reactions, elimination reactions. Okay, so here you will see that oxidative addition between this one. Okay, so this one. So here you will see that O is now O minus and phenyl. So now it is +2 oxidation state. So what is happening here? So this is a nickel. Okay, and so it is actually coordinated like that one. Okay, now it is happening oxidative addition. So here is basically PH and here O, like that. Okay, I hope it is clear now. Now another ppS3 is coming out. So you are getting the vacant position here, so it's become coordinately unsaturated, and then the alkene is coordinated here. So basically the ppS3 coming out and alkene coordination. Okay, very simple to understand. Now the last step, it is very important. Okay, because you are actually making the active catalyst here, because as I told that nickel hydrogen species is the active catalyst. So this one is basically, you can tell it is a pre-catalyst. Okay, but this one is the actual catalyst. So what is happening here, you will see here, this is now the phenyl is here and the alkene is here. So what is undergoing? It is migratory insertion of phenyl to coordinated alkene. So it's basically in alkene, insertion of alkene in metal carbon bond. Here metal carbon means metal phenyl bond. So it's basically what is happening. If you, so in a simple way, so this is my phenyl and here is a alkene. So it is okay. Now this one. So this is basically, now this is the phenyl and this is my alkene. So this is now due to the migratory insertion of the coordinated alkene to here, that styrene will form, and after the styrene, okay, you will get the metal hydrogen species, and the vacant site will be again saturated by the alkene, because here ethylene is in the reactions ethylene is available, and wherever there is a vacant position ethylene will coordinate. Okay, so this is the last step is very important. That is the migratory insertion of the phenyl and the coordinated alkene to make the styrene, that is the byproduct. Okay, and here you will see that styrene will be useful. This is also a good monomer. You know that this is a monomer for the polystyrene, and here you will get that the nickel hydrogen species, that is the active catalyst for the swap process. Okay, so this step is very important because these steps, from these steps you will understand that how we can make the active catalyst from a pre-catalyst where there is no nickel hydrogen bond, because in this part we need a nickel hydrogen bond for oligomerization. In the next slide you will understand why we need nickel hydrogen bond. Okay, fine. Here you will see that how this swap process, that is the first step of the swap, that is the alpha oligomerations takes place. Okay, the oligomerization of ethylene. Okay, now you see that is the active catalyst. Okay, now you have the phosphinoacetate here, that PO, okay, that coming from the phosphinoacetate, and here we have a nickel hydrogen, that is the nickel hydrogen, and that vacant position is coordinated by the alkene. Now what will happen? There will be a migratory insertion between the alkene and the hydrogen. Okay, and you will get the CH2CH3, that is the ethyl. Okay, so you will basically getting the nickel CH2CH3. Okay, from here, and again there will be another vacant position, because what is happening here, you will have a hydrogen and you will have a the alkene. So there, and then there will be vacant position, and this vacant position is coordinated by another molecule of alkene. Okay, and throughout this what will happen, the migratory insertion will be repeated. There will be repetition, let's say n number of, okay, the alkene, then this will grow. Okay, so this is basically, this site is the growing of alkene, alkyl chain. Okay, now these are the alkyl group. Now I have to get back my olefin, alpha olefin. How it will happen? We know that if there is a beta hydrogen, beta hydride elimination is very favorable for transition metals. Now this is my beta hydrogen. Okay, and we know that how this beta hydrogen is eliminated, because these are through agostic interaction. So those we have already discussed in our previous classes, so I will not go in depth. And then it will undergo the beta hydride elimination, that is very important. So here you will see that this will be like that one. So beta hydride elimination, so you will get the corresponding alkene, that is the alkene again, that is the higher alkene, not the ethylene, and you will get back your hydrogen again, and then you have lot of ethylene molecules. Okay, so this deligation, that the alkene steps will be favored, because we have lot of alkene molecules. So this is basically what I am mean to tell, that if you have a like this one, and if we have there is n number of ethylene, then this will drive to the right side due to the last atelier principle, and you will get the and this will be coming out, this one. Okay, so this is, you will see the alpha olefin. Okay, and then again this cycle will be repeated. So here you understand that the important steps and the reactions. If you understood that 4 unique reactions in organometallic chemistry, you will be able to understand without any confusion that one is the migratory insertion, okay, and then you see beta hydride elimination, okay, and from this repeated step of the migratory insertion, you will get the higher number of alkyl groups, and then eventually at the last step, due to the for beta hydride elimination, you will get our desired alpha olefin, and then again this will be repeated, the steps will be repeated. Okay, so so far what we have tried to learn that we need 2 monomers, one is the alpha olefin and one is the ethylene. Okay, now if you remember in the last class we discussed that there is 2 strategies. One is the strategy 1, that is the 2 separate chambers A and B. A is for the oligomerization and B is for the polymerization. Now the strategy 2, that is the tandem approach, there in situ approach. That means the oligomerization and polymerization will be on the same vessel, polymerization vessel, and 2 catalysts, okay, or 2 catalytic centers is better to call. 2 catalytic centers will be operating simultaneously to have our alpha copolymers, okay, alpha olefin copolymers, okay, that is the LLDPE. So here let's assume that one catalyst, that is the catalyst 1, okay, which is, and one is the catalyst 2. Catalyst 1 is the oligomerization catalyst and catalyst 2 is the polymerization catalyst. So now one thing you can imagine that we need two catalysts. One is very good for polymerization and another one is basically the bad catalyst, bad polymerization catalyst, which will be using as a oligomerization. That means that will stop after say like a let's say 8 or 10 number of the insertion, migratory insertion, this one. So let's say it will stop, or the reaction will be slower after 8 or 10 migrations in migration insertion reactions. Okay, so here you will see that in this regard, in the tandem process, where one catalyst will be used for the alpha olefins, synthesis of the alpha olefins, and the other catalyst will be used for the polymerization, okay, the alpha olefin polymerization catalyst. In this regard, these 2 catalysts, you will see that cobalt based sheet based catalysts here again you will see these are the +2 oxidation states, okay, and the similar structure, the code structure, you will see these 2 chlorides and 3 nitrogen. So this is the nitrogen donor N3 type of ligands, and we can name is a catalyst 1, or this is the catalyst 2, and another one is zirconium catalyst, that is the well known systems Kaminsky type catalyst, which is very good for the polymerization, very good polymerization catalyst, that is we already discussed in our previous classes. So now if we can combine these 2 catalysts, either this one, okay, or 1 or 2, or and the zirconium based or titanium based catalyst, which is very good polymerization catalyst, what will happen? Okay. So in here you will see, try to understand that if this is the ethylene, and if we use this one, this is basically this one or that one, any one you can use it, and you will get the alpha olefin. Okay. And in the feedstock we have already alkene is the ethylene is there. So in the same reaction vessel, okay, what we are getting? We are getting the alpha olefin, and we are also adding our well known polymerization catalyst, zirconium or titanium based, whatever that is in your, that is in our hand, and you will get the LLDPE in same in situ. Okay, this one, no, there is no need of two separate chamber, in situ copolymerization. Okay, so this is basically the two catalysts here. Okay, the two catalysts in one pot. So it's basically simplifying the polymerization steps. Okay, and removes the complication associated with the polymerization reactors, and the polymer structure can be controlled by regulating the relative ratio of oligomerization and polymerization catalysts. So it's basically, if I need a higher branching, okay, then we can use little bit more amount of this catalyst, and if I need a short number of chains, we can use the low amount of the oligomerization catalyst. So by the way, we can change the branching in the LLDPE. Okay, so this is a very advanced method, okay, and emerging to remove the complicacy of the strategy 1. Okay, so another one that is very advanced method and advanced development in this area, that is the same catalyst but heterobimetallic center, and here you see that is the two catalysts. Okay, that is, one is the cobalt based catalyst, and one is the, even you can use here the nickel based catalyst also, and one is the zirconium or titanium based catalyst. So you can use for oligomerization purpose, you can use the cobalt or nickel, okay, separately, or here zirconium based or titanium based catalyst for the polymerizations, both combination in situ. And here you will see that we will be using, again, is an in situ approach, tandem approach, but it will be using a single molecules but with heterobimetallic center. Okay, and this the Tobin J. Marx have developed this is quite recent, is developed this very novel catalyst. Here you will see this, we know this is basically CGC type of catalyst here. Okay, we already discussed in our previous classes. I will not go in more detail. I just want to show the design and the advancement in this area. So here you will see that this is a CGC based, and this is the chromium based, that is the +3 oxidation state. Okay, which is attached with a spacer that actually you can vary it. Okay, you can not only you can use the alkyl group or carbon group, you can also use the other heteroatoms. Okay, you can design. So mainly is basically the titanium, okay, and here the chromium, okay, base catalyst attached together, and it's a heterobimetallic system. This one you can, this moiety you can make it very easily from the CrCl3THF3, that is very well known precursor. You can make it in lab without any problem. So here what is happening, you see this is my oligomerization center, this one, and this is the polymerization center. Okay, and this is also one of the very promising heterobimetallic catalyst for LLDP synthesis following the strategy 2. Okay. So this is you'll see that this is in a conclusion. You can we can tell that that alpha olefin polymerization okay, you can approach in two ways. One is the two-step okay method. One is the involving shop process. So it's basically first you make the alpha olefins and then you separate and then you use as a separate feedstock to the ethylene polymerization reactor. And this one you can do in situ alpha olefin copolymerization, and again for this one you can do the two separate catalysts okay, or you can use the single catalyst but it's a heterobimetallic okay. That means actually the two different catalytic centers okay. Okay, single catalyst but heterobimetallic. Okay, and this way we learned how the LLDP are synthesized in industrial process. Okay, so as I told that if we use the Metallocene based catalyst, we can generally tell it's LLDPE. If it is through Ziegler-Natta catalyst or other way, we simply tell it as a LLDP. Okay. So from today's class and the last class, we understood that for industrial purpose, for industrial LLDP synthesis, we follow the alpha olefin copolymerization protocol. So we need to use two monomers. One is the ethylene, that is the main for the main polyethylene skeleton, and to make the linear short chain, we have to use the another monomer, that is the alpha olefin like butene, hexene, octene, but in a lower amount. And to get the alpha olefin, we have to do the oligomerization. So both here oligomerization and polymerization both are important. And for the oligomerations, we have to use the catalysts like nickel based catalysts which involved in the SHOP process, the cell higher olefin process, that is the SHOP. And we can also use a tandem type of approach, which are more advanced and very recent advancement. So here you will be using either two catalysts or the single catalyst with two different metal centers, which are also effective and more advantageous because you can remove the complicacy associated with the two different chambers in the polymerization. So in the next class, we will be discussing how we can what are the another advantageous or how another strategy to make this Metallocene based catalyst to the industry. So we will discuss how you can convert this Metallocene based catalyst for laboratory to industrial process. So you can get an idea that what I mean to tell, that I told that Ziegler-Natta catalyst is a heterogeneous catalyst system, but our Metallocene based catalysts are homogeneous based catalyst systems. The activity is much higher. You can very nicely control the stir regularity, but for industrial process we have to make the homogeneous to convert homogeneous to heterogeneous system for to make the whole process as more economic, and obviously to reuse the catalyst. Otherwise the cost will be very high. It will be not the process will be not economic. So we will try to understand what are the basic steps or logic to make the industrially viable catalysts, or how to convert. And also we will discuss very briefly about the how the polyolefins can be degraded. That is another very important area, okay, because we have to use, now all are promoting, the governments and all the countries are promoting the recyclable and how we can make it, because you know that polyethylene is a very stable polymer, because it is a carbon-carbon bonds, carbon-hydrogen bonds, polar, non-polar bonds, very difficult to break. But how to recycle, how to break, how to make the more useful materials or useful molecules from the used plastics. Okay, so you will be very surprised to know that the same Metallocene based catalyst can be used to break the polyethylene by the concept of microscopic reversibility. Okay, that is another very challenging and very emerging area that should be discussed in this class. Okay, so thank you and see you again in the next class, okay, to discuss about the Metallocene based catalysts. Thank you very much.